Hello everyone and welcome back to the Data Journey YouTube channel. Here in this video we are going to understand how hierarchical clustering work, and we are going to learn how to fit one in Python using scikit-learn. So first, to understand how hierarchical clustering work, let's go to the drawing board just to understand a bit of the concept around hierarchical clustering. So let me draw here two axes, so with two variables. Let's call them age and income. Okay, let me go here and write here age and income. Okay, imagining that these are two variables and imagining that they have the same scale. Okay, just to simplify. Now let me put here some data points. Okay, so I have here some data points. As you notice, these are low income and elderly people, so older people, and these are high income younger people. And here we have two data points that are, let me put this one here, that are very close together, that are low income and younger people. So hierarchical clustering starts, and particularly agglomerative clustering, which is one of the version of hierarchical clustering and the one that we are using, also the one that is widely used in scikit-learn as well, basically begins by combining the two nearest data points in the solution. Okay, so if you look at these data points that we have right here, the nearest data points that we have are these two. I'm going to pick up this distance because this is the first distance that we will plot in another plot that we'll have here, which will be called the distance plot. And I'm going to put here the two data points. Okay, so in this way, let me put the data points in this way, and saying that this is the distance that is connecting them. Okay, what I'm doing right here on the right side is called the dendrogram. This is another thing that we commonly see when we speak about hierarchical clustering. Okay, now these data points should be considered as a single data point, and I'll go here and consider them as a single data point. Okay, we'll see that how we consider them a single data point is related with the type of hierarchical clustering that we are doing, because there are several different ways to link elements or new elements to the other data points. Now, the next step is to calculate the distances, and normally use Euclidean distance between all data points next. And now, for example, I'm going to consider that the next data point, and I'm going to spread these data points a bit farther and choose this one a bit nearer this data point. Okay, so that this is unambiguously the next data points that we are going to connect using this distance as well, which should be a bit larger than the one that we seen before. Okay, so not that large. Okay, this one. Cool, let me also connect them, and these two data points will go here. Now these data points are not connected with these two, okay, because they are still not combined. Okay, they are just connected between themselves here in the dendrogram. Now, an interesting thing is that in this next iteration, we need to calculate the distance between, for example, each data point, even before combining these two. We need to calculate the distance between each data point and this new big data point that is the combination of these two. And how we do that depends on the type of method that we will be using. So if you consider, for example, the average, we'll have the average data point right here. This one is called the centroid method, when you connect this with the middle of the data points. And let me put here new data point right here, and this would be the centroid method, so basically the center of all the data points. Then we also have the average method, which is a bit different. Let me write that in green, which combines and checks the average between the distances of the new data point with the data points that are inside the new formed object. And in this case, we will have thing between the average. It's similar to the centroid. To put it here as the average. And then we have other two, which are the maximum and the minimum. And the maximum and the minimum consider, let me put them in blue, the farthest data point or the nearest data point. Okay, so if we go specifically for the farthest, I'm not going to calculate more distances. I'm just going to put it here. So farthest should be, let me put it maybe in orange or yellow. This is the farthest, and this is the minimum or the nearest. And in this case, this would be the single linkage, and this would be the complete linkage. Okay, this one would be the complete linkage. Now, of course, being the single or the complete depends on the data point that you are comparing to. If you are comparing to a data point that is nearer this data point, for example, one that would be here, and doing that calculation of distance, then this would be the single for that data point, and this would be the complete or the maximum for that data point. Okay, it's always relative to the data point that you are comparing, because when you choose what's the next type of data points that you'll aggregate, you always look at the pairwise distances between all data points. If you already form mini clusters, you'll consider the distance between the data points and the mini cluster. And the algorithm finishes when all the data points are combined, and you will have something like this. For example, put this as distances. So in some ways, this cluster, this one, will connect with this one, and we would have something like this. So when you see a dendrogram, basically just imagine that these bars right here are the distances that we are considering between the data points. We are speaking of a combined version of the data points that go underneath that vertical bar. If we see, for example, here, it would be the combination of these four, which would be something along these lines. So let me go here. When we would combine, for example, these two in some way, let me consider that we would combine them using the centroid, it would be something like this. So this distance would be represented in this plot. So in the end, in the dendrogram, you'll have all the data points here in the dendrogram and the connection between them. This is basically how hierarchical clustering works. We start to aggregate the data points till we have a giant cluster in the end, which will be this cluster right here, that will consider all the data points, but of course that's not very meaningful. In the end, when we have this giant cluster, we've aggregated the entire data points that we see here. We'll see, basically looking at the dendrogram in Python, how we can choose what's a good amount of clusters that we should choose based on hierarchical clustering. If you have any questions about this, you can also check the blog post that I've left in the description, where you can basically check out a bit more about this explanation. Now what I want, let me just delete this, what I want you to take out also from this explanation is that we have several ways to consider a distance when we combine data points, namely single, average, centroid, or complete. This is very important because this is actually a hyperparameter of the model that we will need to choose before setting the solution. Okay, so in this implementation, we are going to use the wine quality dataset that I'll also leave in the resources. It's actually a dataset from Portuguese researchers. Kudos to them for giving that dataset. I also enjoy to show this dataset because we can do interesting things with clusters on this dataset as well. So I'm going to put the dataset here on my Colab. I'll just upload the file by going to load the file to the session. And then here on hierarchical clustering, I have here the wine quality red, and I'm going to upload it here to my notebook, okay, to my Colab notebook. If you have questions about how to use Google Colab, you also have a video on a channel that you can check if you have any questions. Also, if you are having trouble understanding how Python works, feel free to check my Python course in the description, where I teach you about Python on Udemy, and this is an absolute beginner's course. So if you really want to master Python and not only the algorithms, feel free to visit it because we are going deep into the Python language. I'm going to import pandas right now. Here in the notebook, I'll keep importing the libraries as I go by, but again, this is not the best practice. The best practice is to have everything imported in the beginning of the code. In the notebook that I'll provide, or the link for the notebook, you'll see that in the notebook, and the notebook is a bit more organized. Okay, so I'm going to call wine data, it will be equal to pandas.readCSV, and I'm going to do content, basically wine, or I can even go here. I always like to go and copy the path and just paste the path here. Okay, so go here, do copy path, in my case it's in Portuguese, and you paste the path here and you run this one. Okay, so let's see just the head of this data set. So here we have different information about the data set. Oh, of course, and we are missing something. When you see these kind of strange values here, that's because the separator is not correct. The separator here is not a CSV, is this symbol, dot and a comma. I don't remember how this is called in English, sorry. So there you go, we have here information about different wines, and we have the density, sugars, acid, citric, volatile acidity, fixed acidity, different things, the alcohol level, and also the quality of the wine. So higher values mean that the wine has more quality, lower values mean that the wine has less quality. You can also check more about the columns in the link that I provide in the description. Let's fit a hierarchical clustering solution on this dataset. So one of the things that is very important for hierarchical clustering is to standardize data, because we are dealing with distances. Every time we deal with distances in algorithms, remember, important to standardize, even in more advanced models. But when the algorithm is just based on distances, you really need to standardize, because if you don't do that, you're basically giving more weight to certain features, the ones that have a higher range, and that's artificially saying that those features should have more impact in your cluster when they shouldn't. So it's also good to standardize. And here we should go not pre-processing, it's pre-processing, import standard scalar, and I'll do again imports in the middle of the code just for the flow of the video, and I'm going to do standard scalar here, and then I'll actually do scaled wine will be equal to sc fit transform of our wine data. Okay, simple as that. What I'm doing here is applying z-scores to this data, because in that way I'm going to have a scaled version of the data set. If you're not familiar with what z-scores are, I'll also put a link with more info on the description as well. Maybe in the future I'll also do a more in-depth explanation of standard scalar. Let's run this one. Now first I'm going to fit an hierarchical solution using the average method. If you remember, the average method is the one where we compute basically the distance between the data point and the data points that we are combining, if we already have combined data points, and then we calculate the average of those distances. So here, what I'm going to do is the following. I'm going to import first from sklearn.cluster, import agglomerative clustering. And now I have a solution ready to fit, or at least I can use that. Now I can use, for example, average method will be equal to agglomerative clustering, and I'll have to give the following: n clusters equals none, because I'll want to take a look into the dendrogram with all the clusters. If I already know how many clusters I want, I can make the solution stop at that number of clusters, and we'll do that after looking at the dendrogram. Doing that before looking at the dendrogram is a bit non-productive because it's kind of random, and we'll also need distance threshold. Here we'll need to override this argument with 0. Very important parameter is the linkage parameter. This parameter will be the average. This is how we can manipulate which type of distance we will be using here on the solution. Okay, between single, complete, average, and centroid, we've just chosen average. And here we can define our object, and now we are ready to fit it on the wine data scaled, or on the scaled wine, sorry, scaled wine. Okay, we have our agglomerative clustering ready, but now let's first look at the dendrogram and understand how the dendrogram is performing. Just with a few samples, we'll be able to see exactly if the solution is good or not. So I'm going to the notebook that I have to have a function called plot dendrogram, which will be basically just a utility function that will help us plot the dendrogram. That is not officially part of the scikit-learn package, but that is given as a helper. So this is the function that we are doing. We only need to import 2 extra libraries to make this function work: numpy and dendrogram from scipy. So I'm going here at the beginning. Now I'll put them at the beginning. Import numpy as np using the alias, and then using from scipy.cluster.hierarchy import dendrogram. Okay, let's run these two, or with pandas as well, just rerunning it, and now we can define this function. Again, this function is in the notebook that I've left in the resources. Don't need to go through it because really that's not the core of this video. Otherwise, just to go through this function probably take more extra 6 minutes that are precious from your life. And what's important right now is that we look at the clustering solutions. So I'm going to define this function first, and I can plot the dendrogram, and I'm going to do plot dendrogram. Okay, and I'm going to plot the dendrogram of my method. I can pass in the clustering solution I want to plot. I'll also do truncate mode equals to level. This is just something that we can pass to this function, and p equals to 10. Don't need to worry about this right now. Let's just run this because this will give us an idea of how the clustering solution is performing. That's very interesting that we have here, because it seems that this example, the row 151, is very, very different from the rest of the rows. So that's interesting with this method, that we are seeing this. Maybe this is an outlier. We should look at it. This is just a sample of the data points, okay? But immediately we notice that the solution, although we have here, I don't know, maybe 50 examples, or maybe a bit less, 30 or 40, this solution is not producing a very, very good dendrogram, because we would like to have more separated clusters, and this seems to be we have a specific split that we can do. For example, here I'll show you how you can split dendrograms when we have a more clear solution, but there's still, these two clusters are super near, so just by the distances that we have here, I don't like this solution at all just by looking at the dendrogram. Let me try another method. So I'm going to pick up this one, and instead of looking at the average method, I'll look at the single. The single method, remember, is the one that calculates the distance based on the nearest data point when we are calculating this type of distance. And so what I'm going to do right now is to go here and change this to single, okay, the linkage. That's the only thing that I need to do. And I'm going to do plot dendrogram again here. So let's go to plot dendrogram and do single method. Okay, so again, recapping, just pick up the agglomerative clustering result, put single method here just to change the name of the object, and change the linkage to single. Here in the single, as the distances will be very, very short, I can give more examples in the plot, although we will not be able to understand them so much. And I have an error because I haven't done something. I forgot to fit my single method to the data. So I can only plot the dendrogram after fitting the clustering solution and changing the object that I'm creating. Makes sense. But also a good mistake for you to see, because you may make it when going through the notebook. And here, now let's run this again. All right, cool. Now let's plot the dendrogram. All right, so this solution again is not the best, because if we define that we want to define this as the number of clusters, and how do we know how many clusters we have at a specific level of a dendrogram? We draw an horizontal line, and the number of lines that we cross are the number of clusters of our solution. The problem is that if we draw an horizontal line here, for example, in this way, where our distances start to get larger, because these ones are very, very short, we would get 1, 2, 3, 4, 5, 6, 7, 8 clusters. But the majority of the clusters would have 1 or 2 data points. Doesn't make sense, so probably this is not a very good method. So the centroid and average methods would have very, very similar results, if not the same. We only have one implementation of them, which is the average method here in Sklearn. Now, there's another method that we didn't explore there, which is called the word method, okay? The word method basically just tries to minimize the variance of the clusters. And although it's a bit more hard to explain here on the data points, we can use it very quickly here in Sklearn by passing the word linkage method. Now, the word linkage method normally gives much better results, and we'll see why the dendrogram will look different. So let's just change this to word method, linkage equals to word, and then fit a word method here. Let's run this one, and I'll look at the dendrogram, which should be very interesting. Now, let's run this dendrogram as well. And here now, ignore a bit of the samples that we have right here, because in the word method we'll have a lot of samples here zooming in because of the type of distances we are looking to. Even so, this is the coolest example that we see here. Now, let's for example choose this part to divide the clusters, and if you check, this gives a very, very interesting solution, because we would have 1, 2, 3, 4, 5, 6, 7 clusters. Very interesting to see how if we do a cut here, when the distances start to get bigger, and it's a bit qualitative analysis, when we start to see like larger distances in terms of the clustering, of combining the clusters, that's a good solution. But we can cut our dendrogram here, or it would make sense to cut it here. And here, can you guess how many clusters we would have? Pause the video for a minute and see if you can find it. So here we would have 1, 2, 3, 4, 5 clusters. So that's also interesting. Now, in the word method, normally we'll have better shapes in terms of the clusters and better distribution of how the data goes. Let's try the solution with 7 clusters and see how that goes. So I'm going to pick up this one, word method, and I'm going to call it word method solution. Now I have to change something. I can take out the distance threshold and I can say n clusters equals to 7. And this will fit the solution for the 7 clusters. So I'll have the same groupings of the data points that I have right here, but I'll have a way to fit this solution with just 7 clusters and analyze the 7 clusters. Here I have a bug in the code because of probably a typo, so I just remove this one. Now let's run our word method solution. I'm going to the wine data and I'm going to say that the cluster based on this word will be the word method solution, and I can do a fit predict. This will give me the cluster number of the data point. That's something that I want because I want to analyze the clusters later. And here I'm going to do wine data scaled. So I'm fitting on the scale data, but I'll be interpreting on the original data because it makes sense. You always want to interpret based on the original variables, not on the scaled, because on the scaled you lose the sense of reality, you lose the sense of the dimensionality of the data. And if you want to build some business rules, or if you want to apply this to a certain scenario, you would like to not lose that information in terms of the standardization. So let's run this one. And now Google Colab is saying that wine data scale is not defined. That's probably because I've named it something else, of course. I've named it scaled wine. In the notebook that I'm providing, it's called wine data scaled. So just a mismatch of the names. Now let's run this one. Okay, cool. Now on the wine data, if I go to the head of this data set, I'll have a new column called the cluster. You can see here, cluster 4, 4, 4, 0, 4, 4, 5. So now I have for each wine that I have here, I know which cluster the wine is belonging to. Now I'll also want to do something. I'll create here a scaled EF with the scaled version, just because I'll want to analyze a heat map when interpreting the clusters. We'll do that next. And here the columns should be equal to the wine data dot columns until the 12th column, because I don't want to include a cluster. Okay, this is just a data frame that I'm creating. If we go here and see the scaled EF, you would see that this is just to have the same variable names, but here the scaled version in data frame format. Don't worry about it, you'll understand why I'm doing this next. And now I'll want to check the following. I'll want to group by my cluster, and I want to do a mean of all the variables. Now there you go. Now we can see that, for example, the cluster 1 has the highest acidity. We also see that cluster 6 has the highest residual sugar. It's very interesting. That's very, very different from the other ones. And that the higher quality wines are on this data right here on this cluster 2. That's very interesting as well. And now what I'm going to do is go to the notebook just for us to see a distribution of the quality of the wines per cluster. For example, for cluster 6 and cluster 2, and I've called cluster 6 lower quality wines, cluster 2 higher quality wines, we see that, for example, in lower quality wines, we have a very different distribution of sulfur dioxide. So that's very interesting. And if we wanted to build even a supervised learning algorithm for the quality of the wines, we would know that this feature would be probably interesting just by looking at the clusters. Now this clustering solution is a bit odd because I see that some of the centroids are kind of near each other, and it seems hard to separate some of the clusters. So I'm going to go up a bit in our clustering solution, and I'm going to just fit 4 clusters. But first, let me do something. Let me do here an heat map. I'll always like to do this heat map to interpret clusters. I want to import Seaborn as SNS, because I'll want to do a heat map, and for the heat map I prefer to have the standardized version just to have the correct scale on the heat map. So I'm going to do the same here, but instead of writing on the wine data cluster, I'll write on the scale df cluster. Okay, so this one. Now I can have sns.heatmap, and I'll go to the scale df.groupby cluster here, and I'll do a min of the variables as well. This will give me the same information that we have above about the interpretation of the clusters. Just to be clear, what we are saying here, and probably I should have said that in the first place, is that for cluster 0, fix the acidity, this is the average value of fixed acidity for all the examples in cluster 0. Doesn't mean that all of them have exactly 8.6249 and so forth. Just means that this is the average acidity of all the wines assigned to this cluster. The same goes for all the other variables and for all the other clusters. For example, in this one, we know that the cluster 2, the average value of free sulfur dioxide is 17.05. Okay, and this enables us to compare the values or the average values between the variables in the clusters. Okay, it's very, very useful. Now, we are going to do a heat map, but with the standardized values to keep the scale, because we are doing a heat map and that makes sense. Now let's see that. Okay, very interesting. Now, looking at this heat map, when I try to interpret clusters, when I look at an interpretation of clusters, I tend to like more contrast between clusters and variables. And this is not super clear here, although we have here some patterns that we can explore. For example, the cluster 6 has a very, very high residual sugar, cluster 3 has very, very high chlorides and very, very low pH. So we have some interesting stuff here, but it's very hard, for example, to differentiate between cluster 0 and cluster 4 and between cluster 2 and cluster 5. We like to have more difference between them. So what I'm going to do is reduce the number of clusters. I'm going to pick up this word method solution, and I'm going to say that we'll have n clusters equals 4, and I'm going to say word method solution 4. And doing exactly the same, picking up, instead of having wine data cluster, I'm not going to go for the matrix now, I'm going straight for the heat map. I'm going to say in this scale df, I'll have the cluster alternative or cluster alt. I'm going to predict the wine method solution 4. So let me see if this is clear. Instead of looking at the 7 clusters, 1, 2, 3, 4, 5, 6, 7, we are just going to look into 4 clusters, which is this point of the dendrogram right here, where we have 1 on the 50, 1, 2, 3, 4. We can probably try 5 because these two seem that are different, or 3, but I'll want to go 4 to show you something because I think this is very interesting. Now let's go here, and now we can do the heat map on this version. So on the version of the cluster alt, let's run this one. Okay, very, very cool. Now we have significantly different clusters. That's a very, very important thing that I would like to highlight. So notice how we have this variable chlorides, which has a very, very high value on one cluster and low values on the other clusters. This is normally something related to outliers, because I bet that this last cluster, and now I know that this is true, but when I was doing this, I had that impression that this last cluster has very few elements because of just this value that is bringing all those points together. And this is very interesting and something that will happen when you are building clusters and doing unsupervised learning. You should go back after seeing your first solution and remove some outliers based on interpretation. This is also something that I tell to my students at university all the time, that it makes sense to do this. Like, you should go for a baseline first, and then after having a feeling on the clustering solution, you should go back and do some changes. Now let's see if that's the case. For example, going here, scale df dot cluster alt dot value counts, and we notice that the last cluster that we can see here only has 22 wines. So it's probably something related to outliers, and we should treat this variable first before going to the cluster solution, because we are forcing our clusters to be chosen just based on this variable. It may be meaningful for the solution, but 22 examples in a single cluster, it's normally very few, it's normally few examples, particularly if you have more than 1,000 data points. If you have 50 data points, of course that's a lot, but also a clustering solution with 50 data points is unlikely. Okay, cool. So I know that this was a lot of information, but feel free to check the article that I've shared, and if you would like, drop by my Substack, Data Journey, or visit me at my courses on Udemy. Would love to have you there. It was very good to speak a bit about hierarchical clustering and about this method. I hope you've enjoyed this video. Don't forget to subscribe to the Data Journey for more videos on Python and data science. Thank you very much. I'll see you in the next video.